All right, so today we have Xin Wang, who will tell us about the refined BPS numbers on compact Calabi-Yau threefolds from Wilson loops. Take it away.
Okay, thank you. So thank you for the invitation and introduction. Today, I'm going to talk about my recent work about this refined BPS numbers on compact Calabi-Yau threefold from Wilson loop. And this talk is based on work with Xin Wang at USTC and Sheldon Katz at UIUC, and Abrash Khan was in Bo and now moved to Sheffield, and also works about Wilson loops in the following papers. So let me first give an introduction. The key object we will focusing on in this talk is the Wilson loop. So the Wilson loop operator is a gauge invariant operator, and it is non-local, defined as the integral of the gauge field A mu over a closed loop C. So here, this R is a trace over the representation of A mu, and this P is the path ordering for non-abelian gauge theory case. And the expectation value of it gives a measure of quark confinement. For instance, if the value has a parameter loss or area loss, it gives a different prediction for the quark confinement. And in the context of gauge gravity duality, Matassina proposed a string theoretic interpretation of Wilson loops in 4D n=4 super Yang-Mills theory, and reviewing their deep connection to string theory and supergravity. In the past decades, it has been a fruitful approach to study lower dimensional, non-gravitational supersymmetric theories. For instance, starting from string theory, M theory, or F theory, and considering the compactification of them on compact Calabi-Yau spaces, one can obtain supergravity theories, and then decouple the gravity. We can obtain the gauge theories. And so directly compactification of such higher dimensional theories to non-compact Calabi-Yau spaces will also directly give this gauge theories. And many physics actually are explored from this compactification picture or geometric pictures, and many such things are studied. So in the QFT, actually, many conceptual and calculation methods for the refined BPS counting have been proposed. However, the refined BPS counting for compact Calabi-Yau threefold or 4D, 5D, 6D supergravity theory is much harder and unsolved. So in this talk, I will mainly focusing on the Calabi-Yau threefold and the compactification of the such 10-dimensional, 11 and 12-dimensional theories gives 4 and 5 and 6-dimensional supergravity theories. And by considering the local limit or the limit by decoupling the gravity in the gravity theories, we might obtain many gauge theories glued together. And from this, from this theories after decoupling the gravity, we propose a refined Wilson loop structures for the partition functions in the supergravity theories. As I mentioned, so we propose a new structure for the compact Calabi-Yau threefold, which provides a framework to study the refined BPS counting problem in a supergravity theory. And this and our result also provides a refined proposal for perverse sheaf counting in mathematics. So this is the overview of my talk. So the main object I want to study is the 5D supergravity theory, and it can be obtained from M theory compactification. And as I have mentioned, we might use the resulting gauge theory to study and refine Wilson loop structure to study the partition function or the refined BPS counting problem of this 5D series. And this structure provide a general ansatz calculate such refined BPS numbers. And to solve the ansatz, we need some additional inputs on inputs. And the simplest way to obtain such inputs is to directly study some 60 series obtained from F-theory compactification on compact elliptically fibered Calabi-Yau threefold. So this perturbative information of this of the 60 series provide just a few of them provide infinite number predictions in the 5D supergravity theory. This is the outline. In the beginning, I will first review some 5-dimensional n=1 theories, including the theories with gravity and without gravity. And I will also review the concept of Wilson loop and its realization in string theory and M theory, and the calculation method of the web of Wilson loops. After that, I will give a refined Wilson loop structure of a 5D supergravity theory. Then, because I also use some perturbative information from 6-dimensional n=1, 0 supergravities, I also give a review on such theory and possibly their 60 SCFT and little string limits. And finally, I will give a conclusion. To start, the 5-dimensional n=1 supergravity theory we will consider in this talk always comes from the compactification of M theory on compact Calabi-Yau threefolds. So the theory contains 8 supercharges. A supermultiplex consists of a vector multiplex, hypermultiplex, and one gravitational multiplet. And the BPS particles in the resulting 5 series comes from in M2 brane wrapping states on compact 2 cycles, beta in the H2X. And these particles carry spins, JL, in the representation of SU2L and SU2R for the little group of 5D Lorentz group. And the number of these BPS particles, usually denoted as N, JL, and beta, counts M2 branes wrapping state in M theory. And it is always a non-negative integer because of the counting property. And here I also have to mention the masses of this BPS particle is equal to the volume of the 2 cycles is from M2 brane wrapping, where the M2 brane is wrapping on. So after knowing the refined BPS numbers, and actually by tracing over the right spins, the BPS numbers are captured by the topological string free energies in the form of Goba-Vafa invariants. And so the Goba-Vafa invariants are topological invariants with small n labeled by a genus G and the curve class beta. It can be calculated from such expression where the n is a refined BPS number I mentioned, and this is summation over JR is a trace over the right spin contribution. So such Goba-Vafa invariance can be calculated from genus G topological string free energies, which can be in principle calculated from the BCOV's holomorphic anomaly equations. However, so the BCOV's holomorphic anomaly equations is a recursion radius, but to solve it, we need additional we need to solve the additional holomorphic ambiguities, which is usually a hard problem. However, the calculation for the fully refined information of BPS numbers is an even harder problem, because these numbers are usually not topological invariants. They depend on the complex structure deformation of the Calabi-Yau threefolds. So all the traditional methods we used in the topological string theory cannot be worked here. But there are still attempts trying to refine compact Calabi-Yau threefold. So the first one is by Katzclam Panda in 2014. They try to consider the K3 case and the specific and special degree in the K3 fiber Calabi-Yau threefolds based on the modularity considerations. And in 2020, Huang Katzclam also consider a more non-trivial elliptically fiber Calabi-Yau threefolds. And their consideration is trying to give an ansatz for the refined holomorphic anomaly equations. But however, all these works can only show partial information for the refined BPS numbers. However, in the case if the gravity of the 5D theory is decoupled, things become more easier. For instance, let's consider a 5-dimensional quantum field theory by decoupling the gravity of the gravitational theory we mentioned. And usually this means we take a non-compact limit of the compact Calabi-Yau X. So by considering the M theory on the non-compact Calabi-Yau threefolds, the resulting 5-dimensional theories have vector multipliers and hypermultipliers, and the gravitational multipliers disappear in the gauge theory. So here is a rough shape for the local non-compact Calabi-Yau threefold. It's usually contains of a compact contains some compact 4 cycles, like the blue color here, and also some 2 cycles living on the 4 cycle. And this non-compact Calabi-Yau threefolds is usually a cone has a cone-like structure in such a shape. And it's actually more easier to study the refined BPS counting problem in such non-compact Calabi-Yau threefold because we have a gauge theory without gravity. So for instance, from the lower dimensional gauge theory point of view, we have localization method, and the partition function or the instant partition function is an integral over the ADHM instant moduli space. And from the type 2B construction, we also can use the refined topological vertex to calculate the refined BPS partition functions. And also the holomorphic equation for the non-compact case are very successfully refined. And then we can use the refined HAE to do the calculation. And also in the past, maybe past 10 years, and there's a new formula or equation called blow-up equations, also can be used to solve, in principle, all the non-compact Calabi-Yau threefolds that have a 5-dimensional gauge theory correspondence. So in general, the BPS partition. Sorry. Okay.
Quick question on the previous slide, just to understand. So when you said the 5D theories that have some gauge theory correspondence, do you mean that they are like these 5D SCFTs or some of the UV limit of some gauge theory, or do you mean that there is a Coulomb branch description in terms of a gauge theory? What do you mean by gauge theory limit?
Usually I mean Coulomb branch because I want to turn on this killer parameter.
Okay. So as long as you have a Coulomb branch description in terms of some Abelian vector multipliers, you're happy.
Yeah.
Okay, cool. Thank you. So is it not all non-compact, canonical Calabi-Yau threefolds?
Right. So there are a lot of studies, and some people think all of them can be classified from 60 series, but and people get some classifications, but also, I mean, I don't know. I mean, some people don't believe this, but at least from the geometric point of view, I think it's sort of classified in some sense. Yeah. Okay. So yeah. So in general, the 5-dimensional quantum field theory is BPS party. Sorry. For 5D and cos1 QFTs, the BPS partition function is defined as a Witten index by calculating from this expression where the trace is over the Hilbert space of the BPS states. And here the JL denotes the Cartan generators for the SU2L and SU2R I mentioned, which is part of the Lorentz group in 5D. and this curly R denotes the charge operator of the U1 global R symmetry. So one can already see from the definition, the partition function from here requires a global symmetry charge, which is U1 curly R. And however, due to the no global symmetry conjecture in the gravity theory, it cannot be generalized to a supergravity theory because we don't have such a object in the gravity theory. So which means in the refined case, we are with non-trivial epsilon R, like here, we cannot refine this calculation to compact Calabi-Yau case or the gravity case. But for the unrefined case, where this epsilon R is 0, this definition is well defined, and perhaps we can, in principle, we can have a method to do the calculation, even we don't know how to do this at this moment. And the most exciting development in the 5D gauge theory is that the gauge theory can be calculated in a very explicit way. For instance, so this is a structure for a generic 5D gauge theory. The BPS partition function is usually written as a product over the productive part and the incident part. So the incident part in particular for SUN case can be expanded in terms of instantons, and where this mu is a summation over the Yang diagrams, and this Q is the instant counting parameters, and here this means the total number of boxes in the Yang diagram is the instant numbers, and this Z mu is the contribution for each Yang diagram is written like here. So the kappa here is a possible non-zero transients level. Maybe we can set them to some value, and this n mu I mu j are usually called Nekrasov factor, and all these parameters appear here are fugacities like Q1, Q2 are exponential of epsilon 1, 2, and epsilon plus O minus is defined from 1/2 epsilon 1 plus minus epsilon 2, and this BQI is the e to the waves of the scalars in the vector multiplexes, means we're in the Coulomb branch calculation. That's a definition for the partition function, and has been and as has been addressed by Malasina, the insertion of a Wilson loop operator is equivalent to insert a non-dynamic gauge charged and very massive particles. And this is also the main object I want to study. I will mention in this talk. And just from the definition, we call such a particle with a non-dynamic gauge charge and a very massive property as Wilson loop particles. So their equations naturally leads to Wilson loop operator in the path integral formalism. And in this talk, I mainly consider I only consider the supersymmetric theories. So here we also consider a supersymmetric extension of the BPS operator, which is a half BPS Wilson loop operator. So in this case, we have to add a scalar. So the scalar here is also in the vector multiplex to make sure this whole expression preserve half of the supersymmetries. And because I mentioned the Wilson loop operator can be generated by the Wilson loop particles. So this Wilson loop with half BPS property should be generated by a half BPS Wilson loop particle. And they're naturally, and such BPS particles are naturally generated by M2 branes, M2 brane wrapping states on non-compact 2 cycles. So this slide is a basic description of the behavior of Wilson loops, for the waves of Wilson loops. So for a 5D gauge theory with gauge group G, on the Coulomb branch, non-trivial waves phi I, phi R are turning on, of the scalars in the vector multiplexes are turning on. So the gauge group in this case is broken to its abelian subgroup U1 to the R, where R is a rank for the gauge group. And on the Coulomb branch, the representation of Wilson loops becomes a gauge charge of the Wilson loop particle. So we usually can write the representation R in terms of some integer numbers H1 to HR. And the waves has a symptotic behavior like this. So where the phi I is a value for the Coulomb scalars, a vector multiplex scalars. And this dot 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 means the instant correction to this expression. So now I give an introduction for the Wilson loops in M theory construction. As I already mentioned, the Wilson loop in M theory comes from M2 branes wrapping non-compact 2 cycles. So recall that for all the BPS particles in the purely 5-dimensional series, the M2 so they comes from M2 brane wrapping over compact 2 cycles, living on this compact 4 cycles, and from this picture, we can insert some curve class that like this, which is a cone or 2-dimensional object, real 2-dimensional object that intersect with the compact surface, compact 4 cycle here. So there will be naturally M2 brane wrapping over these 2 cycles, and also 2 cycles that has components along here. Because looking at this picture, so the volume of these 2 cycles are infinity, means the particles means the resulting particles in the 5D series would be very massive, and due to the very massive property, all the dynamics should be frozen. So there's no dynamic for such particles. And it is also gauge charged because we require the curve class intersect with the compact 4 cycle here. So the representation I mentioned will be calculated by the intersection numbers among this non-compact 2 cycle over the compact dividers living here. Let me now give an example and also a type 2B description to what I have said, that this will be more easier to give a calculation for everything, calculation to the Wilson loops. So the example I want to first address is the 5D SU2 theory. It can be obtained from M theory on this so-called local P1 times P1. In the type 2B description, it can be described by a D5 and S5 brane system. For instance, we can put 2 D5 branes here among 2 NS5 branes. So here, the NS5 branes is living on is on 0, 1, 2, 3, 4, 5 directions, and D5 branes on 0, 1, 2, 3, 4, 6 directions. And we can now draw the picture for the 5 and the 6 directions over here, and this is usually called a PQ brane web diagram. And here the 5D theory we studied is living on the volume is living on the 0, 1, 2, 3, 4 directions. And there are also PQ strings with some mixed charge, like here is 1, 1, sorry, I should mention PQ branes, and this is the 1, 1 branes, and this is the 1, -1 branes. As I mentioned, the Wilson loops are heavy M2 branes wrapping states, and in the type 2B picture, they should be heavy strings like living on the 5 branes. And actually, to calculate their valves, we can first introduce a fundamental hypermultiplets and then send the mass to infinity. So for instance, here is a PQ5 diagram for the SU2 theory with one fundamental hypermultiplets. And so the brain diagram is by adding additional 5 brains over here. So and there will be some 1,1 strings living on the 1,1 brains with finite mice. And now we send this these 2 brains to infinity. We can have a so the 1,1 string slums is also also infinitely long, and they generate and in this description it generate a Wilson loop operator in the fundamental representation of the 5D SU2 theory. And in one of my work with Qimiang Li and Xin Wang, we use this description and we add more fundamental matters. We successfully calculate the Wilson loops up to 2 tensors 5th order, and we use our result compare with other method like the code mission for defect and agrees. Well, sorry,
that was back to.
Sorry.
No, I just didn't know that I was unmuted. Go ahead.
Okay. So for instance, so the method I have described will give the following result: that the Wilson loop in the representation representation or charge 1, 2, 3 can be calculated by insert such a Wn mu into the localization Young diagram summation formula I mentioned here. We just insert the W mu here, and that will calculate the Wilson loop valves with charge 1, 2, and 3. And we can continue to perform the calculation to infinitely high charges. So now I want to talk about the supergravity theory. From the picture I showed, in a supergravity theory, which is obtained from compact Calabi-Yau threefold X, if we choose a curve class C in the compact Calabi-Yau X, and we sketch the compact Calabi-Yau in the C direction, so at the local corner of the geometry, it looks like a non-compact Calabi-Yau threefold, like we cut this part and throw the remaining part away. So in physics, this corresponds to the weak gravity limit of the 5D theory. And weak gravity means we can actually decouple it, which is a real gauge theory. And the difference here is that this is not a real gauge theory. It's a weak gravity, but the gravity is still there. So the high BPS particles from M2 brains on this curve class C become very heavy along this process. And their dynamic degrees of freedoms are frozen due to this process. Hence, they can be understood as Wilson loop particles in the emergent gauge theory. And the multi-wrapping states over C become Wilson loops with higher representations. So from this physical description, we expect the partition function for the compact Calabi-Yau threefold X can be written as an infinitely summation over valves of Wilson loops in all representations for the emerging gauge series. Like the structure is like this. And this is a partition function, BPS partition function for the compact Calabi-Yau. And this is a leading part, which is a partition function for the local Calabi-Yau of the gauge theory. And this summation over Wilson loops in all representation R. And because the main purpose of my talk is I want to refine this BPS counting because all definition here, except for unknown and ansatz term P, all of them can be refined. So in this way, we can also provide a refined definition. So in physics, this is really easy to understand because maybe we don't know how to refine the compact Calabi-Yau and how to refine the things in the gravity. But if the gravity is weak enough, we can always treat the theory as a gauge theory. So everything would be well-defined in the gauge theory. That's why physically we can refine the BPS partition function with this expansion. And so more precisely, we consider the most general situation that a compact Calabi-Yau threefold contains a curve class C hat, which is a right thing I drew here, and the large volume limit of C hat, where the size of it is very big. The compact Calabi-Yau threefold consists of neighborhoods xi of mutual disjoint connected compact divisors. So in this picture, the compact divisor is the black dot I draw here. And this cone-like things are non-compact Calabi-Yau threefolds, which define and each of these non-compact Calabi-Yau threefold define a local theory Txi, and each xi denotes this non-compact Calabi-Yau threefold. And now we decomposing di into its components, which the sub indices j. And we have the Wilson loop charge, which is defined from the intersection among this curve class C with compact surfaces D in each local Calabi-Yau. And in terms of this compact divisors in each local Calabi-Yau, and a base CL for H2, we can also define the charge matrix. And this charge matrix is one can also usually find it in the discussion of a non-compact Calabi-Yau threefolds. And because here the product, we give a product over delta ij means all the compact surfaces are disjoint. And for suppose for each local theories or for each non-compact Calabi-Yau threefolds, we can calculate the partition function, and we define the partition function for each local theories like this. And they depend on the Kähler parameter. They should depend on the Kähler parameter Tj of the compact of the local Calabi-Yau, and which can be reformulated in the 5D gauge theory in terms of Coulomb parameters phi I and the mass parameters ml. And this Tji are both Kähler parameters in the local Calabi-Yau and also the compact Calabi-Yau. And this expression for the T, I mean, this is the map among this Kähler parameter and the gauge theory parameter phi and m. And according to the physical reason, we arrive at a structure for the partition function of compact Calabi-Yau. That is, this compact Calabi-Yau partition function can be written as a product over the structure I just mentioned. And the reason here is a product because from the viewpoint of each local Calabi-Yau, we should know this Zx can be expanded in this way. So in total, there should be a product like this. And and here, I try to classify the Wilson loops by their charges. And here, this m hat is the effective mass for the Wilson loop particle defined in this way. So the reason we define in this way because I want the mass is a purely mass parameter. So so the curve class which has the same combination in this way intersect with all the compact surfaces with zero intersection number. So now we classify this Wilson loop in terms of its mass. So the mass is also the charge of the Wilson loop. And for each zk, And ZK can be finally expanded in terms of Wilson loops. And here are possible coefficients. So the P function are only functions of epsilon 1, 2, and also some possible dependence on the mass parameters. And we further give a constraint on the expression of ZK, that the ZK is constrained by two conditions. The first one is one-form symmetries. Because ZK is written in terms of a summation over Wilson loops, we require that the Wilson loops in ZK have the same charge under one-form symmetry in each local series. And so here the one-form symmetry can be derived from the Smith normal forms of charge matrix I mentioned, which can be, I forgot to cite papers here, but recently there are a lot of papers talk about the one-form symmetries for 5D gauge series. And also there are, the second constraint is positivity and integrality, which means, so the answers we have written down, like the Wilson loop structure, depends on the gauge theory parameters like the Coulomb parameters and the mass parameters. And if we recover the basis of them to Kähler parameters, the degrees of the Kähler parameters must be non-negative and must be integers. Oh, actually, we also give comments in our paper that this one-form symmetry can be actually derived from the positivity and the integrality condition. So it's a little bit complicated. I didn't give details here. So maybe I should a little bit pause here and ask, are there any questions? Maybe this is a little bit complicated here. Well, if not, let me continue. So our ansatz, I just mentioned before, provides a new framework to compute the BPS partition functions of 5D supergravity series. And with additional inputs on a few refined BPS numbers, we can fix infinitely many refined BPS numbers based on the gauge theory calculation of Wilson loops. And our method actually doesn't require X to be to have an elliptic structure. But if we start with an elliptically fibred Calabi-Yau threefold, we have more inputs from analysis of 60 1,0 supergravity series, as well as their 60 CFT and little string limits. That will make our story more easier. That's why in our work, we only consider the elliptically fibred Calabi-Yau threefold. So for this reason, let me also give a very short overview for the 6-dimensional 1,0 series. A 6-dimensional 1,0 theory can be obtained from F theory on a generic elliptically fibred Calabi-Yau threefolds over a compact surface B. So the circle compactification of the 60 series gives a 5D KK supergravity series. And in the supergravity in the 60 series, the supermultiplets consist of vector multiplets, hypermultiplets, tensor multiplets, and one gravitational multiplet. And their contribution to the partition function in 5D is that the vector multiplets will contribute a spin 0,1. I should say the V vector multiplet will contribute V's spin 0,1, 0,1 spins 1/2 BPS states in 5D. And this hypermultiplets will contribute 0,0 BPS states. And this tensor multiplier contribute 1,5 and contribute 1/2 and 0 spin BPS states. And this gravitational multiplier contribute 1/2 and 1 BPS states. And another thing is that matter contents of the 60 series are highly constrained by the anomaly cancellation mechanism. So for instance, the most simplest one is that the number of hypermultiplets minus number of vector multiplets is equal to 273 minus 29 times t, and t here is a h 1,1 of the base minus 1. So for instance, consider X is an elliptically fiber Calabi-Yau threefold over P2. Because the P2 H11 is 1, so the number of tensor multipliers is 0. And because we consider smooth elliptic fibration, there's no gauge group, there's no vector multipliers, it's also 0. And so the number of hypermultipliers is 273. So this geometry has two Kähler parameters, and one is for elliptic fiber, and another one is for curve class in P2. Denotes their curve class degrees as DE and DB. From what I have described, the perturbative contribution in the elliptic fiber direction, D is such contribution. So the first one comes from the gravitational multipliers, and this is a tensor, vector, and hyper. So from this analysis, we can obtain this spin contents in the fiber direction like this. So from this single input and our Wilson loop structure formula, we can, in principle, compute all refined BPS numbers with degree D fiber, elliptic fiber smaller than 3, and for arbitrary dB, except for this one because this is the neutral charge and it has 0 intersection number with P2. For instance, we solved the refined BPS numbers, and this is the two tables for elliptic fiber degree 1 and 2. And from the table, one can already see that all of the numbers are first integers and then negative. And we also check that all these numbers agree with the overlapped refined GV numbers proposed by Huang Clam in 2020. And I also checked in the unrefined case where we can calculate more numbers. The result here also agree with the Jacobi form conjecture for the elliptic fiber Calabi-Yau threefold. And we also studied many other examples. For example, the 60 theory with non-abelian gauge groups. And the one I would like to address is the 61,0 theory with gauge group G2 over the Hertzsprung surface Fn. So where this G2 gauge group is living on the minus n curve in Fn. In the 60 super SCFT limits, this supergravity theory becomes a 61,0 G2 theory with some fundamental hypermultipliers. And this theory already studied in 60 CFT case can Higgs to 60 SU3 theory. So the Higgsing process is that we turn on a mass for one of the hypers of G2 and makes a mass of the G2 hypers has a non-trivial value like epsilon r. And from here we can explicitly see that this Higgsing and as also correspond to the complex structure deformation calculated by one of my collaborator Sheldon Katz. And so from here we can explicitly see the change of refined BPS numbers in the refined case. So interesting thing here is that in the unrefined case where epsilon r is 0, so this Higgsing process doesn't change the number because we just turn a 0 value to a 0 thing. Right. So finally, let me give a conclusion. So in this work and in our work and in this talk, we are interested in the 5D supergravity theory obtained from M theory, and this theory the BPS partition function of these 5D theories usually studied by the topological string on some compact Calabi-Yau threefold. but this correspondence cannot give a calculation for the refined BPS states counting problem, refined BPS counting. And by considering the limit of decoupling gravities, we can study its emergent gauge series, and from the emergent gauge series, we give a refined Wilson loop structure for the partition function over here. And furthermore, in our papers, we focus on the 5D series, which are KK series of the 60 supergravity series, compactified on a circle, and where they give more inputs. And we also find a typical example. We can actually see the dependence of the complex structure deformation for the refined BPS numbers. Right. Okay. Thank you for your attention.
All right. Do we have questions? Yeah, it seems to have been very clear. Then in that case, I would say let's thank Xin again.
Yeah,
and we can go off the record if there are some questions that people don't want on the recording.